Welcome back to another Explainer. Today, we are unpacking the completely invisible mechanics that literally run our physical world. From the massive planetary scale of the sun heating the Earth, right down to the appliances humming away in your kitchen, heat dictates how matter behaves. But how does it actually interact with the physical stuff around us? Well, that is exactly what we're going to explore today as we dive into the thermal properties of matter. Let's kick things off with a little mystery hiding in plain sight. Have you ever walked over a bridge, or maybe looked closely at railway tracks, and noticed these small, deliberate gaps? It seems totally counterintuitive, right? I mean, why in the world would engineers intentionally leave breaks in a track that's meant to carry high-speed trains weighing thousands of tons? Well, it turns out, those gaps are absolutely crucial, and understanding why is the key to unlocking today's entire topic.
Now hold that thought for a second, and think about a completely different scenario. Your morning routine. You're stirring a steaming cup of coffee with a metal spoon, and within seconds, the handle is almost too hot to touch. What do heavy-duty railways and your morning coffee actually have in common? The exact same branch of science.
Okay, let's dive into this. What we're really talking about here are the thermal properties of matter. Think of this as the fundamental rulebook for how materials behave whenever they gain or lose heat. Whether it's solid steel, liquid water, or literally the air in the room you're sitting in right now, everything in the physical universe reacts to temperature changes based on these exact principles.
So what actually happens when you add heat to a material? Matter typically responds in one of four ways. It might increase in temperature, physically expand in size, transfer that heat to other objects, or just undergo a complete change of physical state, like melting or boiling. This right here is our roadmap for today.
Let's break these down, starting with thermal expansion. The really crazy thing here is just how universal this rule is. Most solids, liquids, and gases expand when heated and contract when they cool down. Imagine a solid metal rod. When you heat it up, its particles get energized and start pushing further apart. It's this invisible micro-level dance that causes visible macro-level growth. In fact, this exact principle is why the Eiffel Tower actually grows a few inches taller every single summer.
Next up is heat capacity, which is simply the amount of heat required to raise a substance's temperature. Think about boiling a massive pot of water versus heating up a tiny piece of metal. Water requires a staggering amount of thermal energy just to raise its temperature by a few degrees. Different substances basically have different appetites for absorbing heat before you actually feel them get hotter. And this brilliantly illustrates our third property, thermal conductivity. This is all about how well a material passes heat along. Conductors, like metals, are incredibly efficient at moving heat quickly, which is exactly why that metal spoon got hot so fast. On the flip side, you have insulators. Materials like wood and plastic stubbornly resist the flow of heat, acting as these really reliable thermal barriers.
Finally, we've got the most dramatic property of all, the change of state. By continually adding heat, you can actually force a material to change its very form. Solid ice absorbs heat to trigger melting, becoming a liquid. If you keep adding heat, that liquid water reaches its boiling point and transforms right into a gas. It's this incredibly linear progression driven entirely by thermal energy.
So how does all this theory actually play out in the real world? Let's solve those mysteries from earlier. Those gaps in the railway tracks? The crucial point is that they are expansion joints. Because of thermal expansion, steel tracks and massive concrete bridges physically grow on hot days. If engineers didn't intentionally leave those gaps, the expanding materials would just buckle and cause catastrophic failures.
And what about that crazy hot spoon in your tea? Well, we purposely harness thermal conductivity every single time we cook. Our pots and pans are made out of strong heat conductors, things like copper, aluminum, and iron, to transfer heat from the stove directly to your food as fast as possible. If we tried making a frying pan out of an insulator like wood, well, aside from instantly catching fire, it would make for a terrible breakfast. But you know, sometimes we actually want to stop heat dead in its tracks. Enter the trusty thermos flask. A thermos cleverly engineers the properties of insulators to drastically reduce heat transfer. It creates a physical barrier where heat just cannot easily flow. And that simple but honestly brilliant manipulation of physics is exactly what keeps your coffee piping hot or your ice water perfectly cold for hours on end. Even the massive household appliances sitting in your house right now rely entirely on these principles. Believe it or not, refrigerators and air conditioners don't actually create cold. Instead, they painstakingly control heat transfer, using mechanical systems to absorb heat from inside a space and forcefully dump it outside. We are essentially manipulating thermal properties to our everyday advantage.
All right, to wrap things up, let's look at the main takeaways. Thermal properties are the master rulebook for how matter responds to heat. They dictate temperature changes, physical expansion, heat transfer, and state changes. And as we've seen, these aren't just abstract textbook concepts. They are the invisible mechanics that are absolutely essential to structural engineering, global transportation, your household appliances, and the everyday tech we all rely on.
Which brings us to a pretty fascinating final thought. We've seen how heat governs everything from heavy-duty railways to your kitchen stove. So I want to leave you with this challenge. Look around the room you're sitting in right this second. How many thermal properties are at work around you right now? From the insulation in your walls to the electronics warming up on your desk, the invisible mechanics of heat are constantly shaping your world. Keep exploring, stay curious, and always keep looking for the science hiding in plain sight.